Okay, welcome back to MacNab Chemistry. Today we're going to have a look at the trends in physical properties of group 7 elements, also known as the halogens. Okay, so we're going to look at the trends in physical properties of group 7 elements, also known as the halogens. Okay, the group 7 elements that we need to consider are fluorine, chlorine, bromine and iodine, and the physical properties we need to consider are firstly the trend in electronegativity of the halogens, and secondly the trend in boiling points of the halogens. Okay, if we have a look at our table of data here, we can see that the elements that we're going to consider are fluorine, chlorine, bromine and iodine. We can see that as we go down the group, the atomic number increases. We can also see that as we go down the group, the atomic radius increases, and as we go down the group, the radius of the halide ion increases. As we go down the group, the boiling point increases, and as we go down the group, the electronegativity decreases. So electronegativity decreases as we go down the group. Okay, so first of all then, let's have a look at the trend in electronegativity of the halogens. Okay, first of all then, remember that electronegativity is the power of an atom to attract electron density in a covalent bond, or electronegativity is the ability of an atom to withdraw electron density from a covalent bond. Okay, the data shows then that the electronegativity decreases as we go down the group. Okay, so to explain this we need to consider three factors. Okay, the first factor we've got to consider is the atomic number, and as this increases, then the attraction for the bonding electron pair in a covalent bond would be expected to increase. Okay, however, we must consider the number of electron shells, which is the shielding. As this increases, the outer shell electrons become more shielded from the nucleus, making the outer shell electrons less strongly attracted. Okay, so we've got to consider atomic number, okay, the amount of shielding, and then the atomic radius. Okay, the attraction between the oppositely charged particles falls rapidly as the distance between the nucleus and the outer shell electrons increases, resulting in the outer shell electrons being attracted less strongly. Okay, so these are our three factors. I tend to refer to this as the sound factor. Okay, your shielding, if I can get that on the page, yeah, the shielding, the atomic radius and the nuclear charge. Okay, so the shielding, atomic radius and the nuclear charge. Okay, those three factors help to explain the changes in electronegativity of the halogens. Okay, so the electronegativity of an element depends on a balance between these three factors. Okay, the decrease in electronegativity of the halogens as we go down the group shows that the increase in shielding and the increase in atomic radius more than compensate for the increase in nuclear charge. So your increase in shielding and your increase in atomic radius more than compensates for your increase in nuclear charge. So basically, from the SAN, the S and the A outweigh the N. The shielding and atomic radius outweigh the nuclear charge. Okay, something else that's worth noting here is that the large electronegative value for fluorine means that the bond between an element and fluorine is more likely to be highly polar than a bond formed between the same element and the other halogens. Basically, fluorine is very electronegative, so therefore other atoms that are bonded to fluorine, you tend to get a big dipole across the covalent bond. Okay, and we've seen that when we've discussed hydrogen bonding earlier in year 12. Okay, so that's the explanation for how electronegativity changes as we go down group 7. Okay, the second physical property that we need to look at for the halogens is their trend in boiling point. So number 2, we need to look at the trend in boiling point of the halogens. Okay, so firstly we need to remember that all halogens exist as diatomic molecules. So fluorine actually exists as F2, chlorine as Cl2, bromine as Br2, iodine as I2. And within the element, okay, each molecule is attracted to other molecules, or each molecule is attracted to other like molecules by weak intermolecular forces, also known as van der Waals forces. Okay, and if we remember back to when we learnt about van der Waals forces, we'll know that bigger molecules are more polarizable. Okay, so therefore the bigger the molecule, the larger the temporary induced dipole-dipole attraction, therefore the higher the boiling point. Okay, so larger molecules are more polarizable and have a higher boiling point. Okay, so iodine has a higher boiling point than bromine, which has a higher boiling point than chlorine, which has a higher boiling point than fluorine. Okay, that's it for today. I hope that's been helpful. Thank you for watching, and don't forget to like and subscribe and click on the bell notification to stay updated.